for the introduction. As I said, my name is Barry Dillon, and on behalf of my co-authors, Antonio Lawrence and Bill Herrera, I'm missing some slides, so can we give that a second? There we go. I'll be presenting the paper Advertising Bootstrapping Revisited. However, before we can start talking about advertising bootstrapping, before we can start talking about first we have to talk about a little bit of basics. A little bit of fully homomorphic encryption. In a fully homomorphic encryption, generally it is our intention to take multiple messages, encrypt them, and then do operations on the encryptions. And what comes out is the operation done on the underlying messages in an encryption. However, when we do this, there is often a significant problem, and the problem is that this has a significant amount of noise. To see this, we can take the tautological example, for example, LWE encryption. As we can see here, we are encrypting message M under a secret key S, and that introduces some noise E. This can only be decrypted if the noise at the end is significantly is low enough that it runs to zero. When we add two ciphertexts together, that is not a problem whatsoever. This is a linear growth, but once we go to multiplication, we get an exponential error growth. And this is unmanageable. So we introduce bootstrapping, an algorithm which allows us to reduce the noise of the ciphertexts as we do multiple computations after each other. There are two types of bootstrapping. The first type of bootstrapping is the one here on the left. What we do here is we bootstrap after every operation with every ciphertext. This is usually very fast. We can make this very fast, but the problem is that the costs are per bootstrap. So that means that even if we get a lot of ciphertext together, we don't win any speed. The second type of bootstrapping is batch bootstrapping, where we take a lot of ciphertext, smash them all together, do one massive bootstrapping, and then get all the bootstrapped ciphertext out again. This is usually a lot costlier than the first method, where we use the gate bootstrapping, but because we are doing multiple ciphertexts at once, we can amortize the bootstrapping cost. However, there is a third type. This was introduced by Vicencio and Sorel in 2018, who introduced a batch bootstrapping type using very similar techniques to the fast bootstrapping types over here on the left-hand side, the gate bootstrapping techniques to improve the quality and the effectiveness of their batch bootstrapping. In our paper, we then also present a new version of such a batch bootstrapping technique, the third type, where we combine both techniques. And that is what we are going to be looking at today. To achieve this, we will go through a few well-established steps, although I will be leaving out a lot of the details and focusing mainly on the interesting bits, really. The first thing we want to talk about is packing. So, as I said, we were going to try and get a lot of different ciphertexts all together and then out and then bootstrap them all at once. For this, we take all the host and LW ciphertexts and we throw them into a ring LWE ciphertext. Ring LWE is very simple, LWE, like overlays. What we then do is we take this ring LWE ciphertext and we use an intermediate scheme as a bootstrap scheme. So we transfer now from ring LWE to a scheme introduced by Gentry, Sahai, and Waters called GSW. For GSW, we have encryptions over a ring, and these are polynomials, and these are encrypted in the following way, where G is a gadget vector, which is a tensor product of the two-dimensional identity vector and a gadget vector. The power of the GSW scheme is that we can use an accumulator to take a lot of information into one single element, which is, as the name suggests, accumulator. We can see this, for example, if we have an LW encryption and we built the accumulator as an encryption of a GSW encryption of a specific element. In this case, we call it T of X times X to the V. Well, then we can multiply all the AI times SI onto it as an the AI times SI that comes from the LW encryption. We can then get this value and multiply it onto the accumulator. And once we do that, we actually come out with a GSW encryption under some key S hat. That is just an encryption of T of X times X to the delta M plus E. Having done this, choosing our initial vector correctly, the T of X, we can actually obtain something much more interesting, a GSW encryption not of X to the power of delta M plus E, but just an encryption of X or delta M plus E. This does cause a fair few problems. The first one we're going to look at is this one. In FAG, we do a lot of our work in the FFT or entity space, which means that we take our ciphertext, we transform it into the FFT or the entity space. That is where we do all operations, and then at the end, we take the whole thing back to the normal space. That is very hard to do, not particularly because of where we are, but because we are using GSW. GSW uses a modulus that is extremely large and doesn't fit in any the native integer sizes of the processor. So instead, we are going to play around a little bit, as we do. We take our GSW, which we will define for Z modulo Q, modulo X to the P plus 1, where P is prime. And to be able to do the FFT transform, we will claim that P is always congruent to 1 modulo 2n. We can then use a special technique called the double CRT form by using the decomposition theorem, which uses the Chinese Remainder theorem to split Q into individual primes, the small QIs, which actually do fit in the native integer types. Which is all fun and games, but we don't know if every element in a polynomial ring can be represented in such a double CRT form. Well, it can. We take a polynomial A, and then for A of X, for A with coefficient vector A0 to AN minus 1, we can define the matrix of A as the entities taken for each of the small QIs on the A of X modulo QI, and that actually gives us a nice and neat looking matrix. This matrix does preserve the homomorphic operations that we are looking for, because addition and multiplication are now just pointwise addition and pointwise multiplication of the matrices. There's only one slight issue. We just introduced a gadget matrix, and that gadget matrix is now broken. It does not work, so we're going to have to make a little bit of a definition. Let Q then decompose as in the first line, and let D be the number of digits. Assume that D divides L in that K be equal to L divided by D, then for 1, that's equal to I, that's equal to D. The ICRT digit is given by DJ, such that DJ is product of K consecutive primes. We can then define QI, big QI, as Q divided by the DI, and we let QI hat be Q inverse modulo DI. This scaled gadget matrix is then given by the formula in the middle, where the alpha I and alpha mod DI. This is in fact, as the last part says, a gadget matrix, so it's an inverse wall operation. At which point we come to something that is very interesting. something that is a very normal operation in GSW ciphertext is called ciphertext shrinking, where you take the least significant bits of the ciphertext and you can throw them away. However, in the double CRT version of the GSW, that is not possible. Because in the double CRT version, there is no such thing as least significant bits. That concept just doesn't exist. So we have to think about something, and that is where we have to find our shrinking algorithm. This allows us to play with the gadget vector and with the ciphertext to still obtain a shrinking algorithm which removes least significant bits. Really, all it does to start with, see your pointer. Really, all it does to start with is it makes some preliminary computations similar to what we saw for the gadget matrix, and then rearranges the ciphertext in a specific way where it can remove k rows from both columns. After that, we obtain a matrix with a wrong scaling element. So alpha is no longer fitting. Therefore, we have to mod switch each of the different rows instead of just dividing to obtain a new scaling factor for us to be able to continue working with the shrinked ciphertext. The shrinked ciphertext is a very important part of this because it allows us to have a cubic and performance improvement in all 4 homomorphic operations, which significantly impacts the efficiency of the outcoming bootstrapping procedure. So now we can go to the entity space and we can do our operations there. We can shrink our ciphertext. We can even do stuff like key switching. We can modulus switch. The one thing we can't do yet is go back, because we are working in a ring with negacyclic polynomials. There is no inverse operation from the entity space to the normal space that preserves the homomorphic structure. Of course, I wouldn't be mentioning this if we don't also provide a solution. First, recall that our polynomials are defined modulo on ZQ modulo x to the p plus 1 of p is prime and p is congruent to 1 modulo 2n. Well, the reason we want that is because then we know that there is a 2n root of unity, which we call psi, with the power vector of those roots of unities being all psi. Normally, in the cyclic polynomial case, we would obtain a very manageable, nice operation where we can go to the entity space and not out of the entity space, and all we get is this product of n. That doesn't work for the data cyclic polynomials. Instead, we have to do a little pre-processing. So before we go to the entity space, we decide to multiply pointwise by the power vector of the roots of unity for both a and x. Then we go to the entity space, we invert the entity, and then we multiply by the inverse of the power vector again to obtain a very similar result. What you might notice, if you're familiar, you see here that we're working modulo 2n, but our NTT is of degree n. And that is because we managed to get that saving. So we only have the dimension n NTT, despite working modulo 2n. This also allows us to keep the inverse entity to only a complexity of O n log n instead of 2n. So the nice thing about this is that we can now move on to the bootstrapping algorithm. So we take this input, we take n LW ciphertexts. First thing we do is, as I said, thank you. Then we can get a little bit of packing done. Once we've packed, all we need to do is play around a little bit. So we're starting here at line 2. First, we do that multiplication, that pre-processing. Then we use gamma automorphisms to obtain ciphertexts, which are GSW ciphertexts, which encrypt x to the minus ai times the key. but now the key has changed. So to remedy that, we quickly do a key switch to obtain the old key back. And then because B is a known public element, it's very easy for us to just compute x to the BI times this ciphertext here to obtain the ciphertext x to the BI minus AI times CI. Doing this for each of the ciphertexts, we obtain, and then inverting the entity, we actually obtain an output of new ciphertexts under the secret key S, K, which are all LWE ciphertexts. This obtains, to our knowledge, the first and currently only implemented amortized bootstrapping protocol relying only on polynomial approximation factors. In the final minute, I do want to talk about what this technique concretely obtains compared to previous works and what it sets as a benchmark. For this, let rho be the depth of the entity and let n be the dimension of the LWE scheme. Then we can see that compared to the work by Vicencio and Sorel here on line 3, we actually save a massive 3 to the row in our total cost. We can still bootstrap all of them. That's just the amortized cost is just, it saves, yeah, again, the 3 to the row factor, and even our noise overhead is a lot smaller. What does that mean more specifically? Well, before I go into that, let's first have a quick look at what it means, what shrinking does for us. Compared to without shrinking, the shrinking has a minimum speed up of 1.5 for our scheme. So it is extremely important. The larger the ciphertext you get, this also starts ticking up very, very quickly. Compared to other work, we can then see that for the prime 12289 with N1024, we have a speed up of 3.4 times compared to the work by Vicencio and Sorel. And for L equals D equals 4, we have a speed up of 1.7. So even relatively speaking, compared to other work, we are in very good hands here. Implementing this wasn't an absolute crime, but the code is available online. Links on the next slide. As a final thing, I want to mention that the failure rate of the amortized bootstrapping protocol has a failure rate of 2 to the minus 22 for 7-bit integers, but for 8-bit integers, this goes up to 2 to the minus 7. Thank you very much. There will be some questions.
Recently, I noticed that in your, I guess, 2023, in a paper from Han Wang and Hong Hao Liu is also by using Dream as the WE to do some bootstrapping. So have you compared with that work? Okay, we'll give some comments or remarks on their work.
Their work is absolutely visionary. I think it's really good. I've read the work, as have my co-authors. The biggest problem that we have observed is that their work might not be implementable. So their work is mostly theoretical. Therefore, comparing to their work is very difficult until we see an actual practical implementation where we can actually compare numbers more rigorously.
Okay, thank you.
So it seems your work relies heavily on the ring with modulus x to the power of p plus 1. And I want to ask, have you considered using other modulus, like, for example, power of 2 cyclotomic rings or other points?
Yes, so we have considered using power of 2 cyclotomic rings. This is also what is considered in Vicencio Sorel's paper. The big problem with that is then that the application of the discrete Fourier transform or another theoretical transform is impossible in a direct manner, and you have to rely on obscure other transforms to be able to obtain the same result. So just to quickly go back, the reason that we in the 2018 see a power 3 to a row is because they had to use a base 3 new style transform just to get everything to hang together. And on top of that, they have to do some extra work. By restricting ourselves to the rings modulo x to the p plus 1 or p is prime, we avoid that and can use the FFT and entity directly. Thank you.
Thank you.
I want to ask the implementation question. Do you have some suggestion how to implement the switching key of the Galois automorphism?
Sorry, could you say that again, please?
And how to implement the key switching key of the Galois automorphism?
So if you're looking at for specific concentrated implementation questions, I would heavily suggest checking out our implementation, which is not linked. Let's take it offline. I'll get you the link to the actual implementation and the email to the person that implemented it. He will be much better at giving you a serious answer than I am.
And also another question I want to we also propose our new gadget matrix. Yesterday talk, Joyone proposed that the constructor or usual techniques to propose the square gadget matrix. If your gadget matrix can be used to construct a better
I'll be completely open with you. I was not aware of this work until the presentation. It is a very interesting work, and it's definitely something to look at for follow-ups.
Thank you.
Any other question? I have a quick point about ring vectors. There are several techniques to create this one. Choose which one to choose.
Generally, so me coming more from the theoretical side, use whichever one is more efficient. I believe I wouldn't dare say which one we've used in the actual implementation specifically.
Okay, so let's next for you. Sorry. And so the talk is about rotation distribution of systems. And this is very important with Johnson Lee, Young-Sik Kim, and Johnson Lee.
I'm very glad to give a talk for our paper, and my talk is about the rotation key reduction for the client server systems of embedded network, including the application. So I'm Juno Lee, the presenter of this talk, and this is the result of the four joint work with Juno Lee, Sang Lee, Young-Sik Kim, and Johnson Lee. Yeah, so outline is this. So I will introduce this rotation key problem in the coding application. Usually I focus on the BFV and CKTS. And I will propose the hierarchical rotation key system and algorithms. And then I propose the efficient rotation key set generation algorithms. And I will show the simulation results for these proposed algorithms. So
I explain the rotation key problem. So the fully homomorphic encryption is, as you know, the fully homomorphic encryption is the encryption schemes of performing arithmetic operations such as addition and multiplication, and it can solve the privacy issue of the outsourcing computation such as the genomic analysis and cloud service and AI as a service system. Because this is there is a conflict between the privacy and services, so the fully homomorphic encryption can solve this conflict. There are three types of the FHE, the bitwise FHE, and integer value HE, and the real value HE. So there are two important schemes, the BFB and CTK scheme. This is very similar scheme, but it deals with the different data type. So I will deal with the BFB and CTK scheme in this video. So I focused on the rotation operation in the BFB and CTK scheme. So the reason why we need the rotation operation is because of the packing. The packing means the multiple data in the one cycle. It means that if there is a CT, the ciphertext, then this CT ciphertext is encrypting the multiple data, multiple integer or multiple real number, M0 to M-1. And there is another important characteristic in this scheme is the single instruction multiple data, the SIMD. The SIMD means there is a homomorphic addition and multiplication, and in this, if we perform this addition and multiplication, then the whole data in the ciphertext is simultaneously added and multiplied for this one homomorphic addition and multiplication. So we have to note that the same location, each element of the same location is added in multiplication for this homomorphic addition and multiplication. So the packing structure is in the CFP and CTK is very similar, but slightly different. The BFB is encrypting the matrix 2 by n matrices. So, and the CTK scheme is one-dimensional vector for the complex number. The BFB scheme is integer for modulo P. So, the reason why we need the rotation operation is like this. We need operations with the different location. The different location means the M0 plus T1. The M0 means the first element, for example, the M0 means the first element in side 1, first side text, and the T1 is the second element in the second side text. But the homomorphic addition only add the first element and first element in the different side text. So if we perform some such as convolution or bootstrapping or matrix multiplication, then these operations with the different location is needed. Another operation is the operations in the one-sided text, such as the M0 plus M1. This is in the side one, same side of text, but it has to be added. Then the rotation operation is needed. So the rotation operation means that the homomorphic cyclic shift. The cyclic shift is all elements is moved by the R shift, R left shift. The left is the conventionally default direction. So in the BFB scheme, there is also rotation, but the rotation means the row rotation. In each rotation, we will cyclic shift by R shift when we perform the rotation operation by R shift. The column rotation is just stopping the rows, so this is not the stop of our. And the rotation operation in the CKK scheme is very similar to the BFB scheme, but there is one row in this CKK scheme, so it is similar to the BFB scheme. to perform the rotation operation. So I will explain the rotation key problem. The main problem is each R-shift rotation operation requires separate rotation key to different rotation key. So rotation key means the evaluation key, a kind of public key for the rotation operation. So the server should have the rotation key for this corresponding rotation operation. But if R1 is not the same as the R2, then we need different rotation key, RK-R1 and RK-R2, which is different from each other. So this separated rotation key should be generated and transmitted by the client because the clients have the secret key. Because the rotation keys have to be generated by the secret key. So let's see the diagram. This server have the computing model, and this computing model have some rotation operation, R1 through RK, shift rotation operation. But this rotation operation requires the rotation key for each rotation. So the clients have to generate these corresponding rotation keys, all rotation keys, and then this have to be transmitted. And the server receives this all rotation keys from the clients. Then the computing model can be evaluated with the Homomorphic equation. So if there is many rotation keys in this computing model, then the key generation in the client, the runtime of the key generation in the client, and the transmission is very heavy. So if we evaluate some artificial intelligence model, so this is very complex model. So what if many types of rotation operations are required in the complex computing model, such as SCNN model or transform model? So previously, in the ICM 2022 conference, there is some CNN implementation with the CTK scheme. And there is some with this implementation technique, the resonant native CNN model can require 617 rotation keys, rotation shifts. So let's see the example of the resonant model. So assume that let's assume that the client have a PC with without any accelerator with only CPU, and the server has this high performance GPU devices. But the client have to generate this rotation keys from the security. So if the client generates all rotation keys, then this generation of the rotation keys by clients, it takes 145 seconds, which is too low for clients. And the transmission is somewhat more severe. This is 15 gigabytes. But this is very heavy communication for the clients. So we want to minimize the burden in the client because there is two reasons. First, the client is the client. The clients usually do not want to compute much. And the second is there is no high performance devices in the client side. So if possible, the server which has the high performance GPU and willing to, so this is the service provider. The role of the server is service provider. So the server is willing to take some burdens for the clients. However, the rotation keys should be generated in the client side with the security. So this is the main problem in our paper. And there is one trivial solution. The trivial solution in the previous papers is using the fact that the R-shift rotation can be composed by the several power 2 shift rotations. For example, if we want to 13 shift rotation operation, then it can be evaluated with the 3 rotation operations. One shift rotation, 4 shift rotation, 8 shift rotation. So if we increase this number of rotation operations, then the power of 2 rotation key set is enough to enable all types of rotation operations. Because all numbers can be summed with the power of 2 integers. So the rotation keys can be reduced, but the latency of the whole computation model in the server is significantly increased. So we simulated the computation time, and this 2.2 times slower. So we do not want to increase the runtime of the whole equation. So the main question is how to reduce the computation and communication for the rotation keys in the client while the runtime of the homomorphic computation in the server remains the same. So we want to satisfy these 2 conditions. So this is our problem, and we solve the problem with this hierarchical rotation key system. So the main concept is the method for the server to generate all required rotation keys without any secret key. So if the server can generate the rotation keys by itself, then the client does not have to generate all the rotation keys. So the concept is the diagram. This is the previous key generation. So the client to generate all required key for the server, then transmit, and the server has to store this rotation key set to apply the service. But this our idea is the proposed key generation method is so so-called speed of the key generation is only generated and transmitted from the client. And then the server can generate some rotation keys, one required rotation keys from this small set of the seed. So it can compute the same homomorphic computation without any increasing the number of the key switching operations. So we constructed this key generation with the hierarchical rotation key generation. So the code plan generates the small number of rotation keys. These rotation keys will be explained. So I explained with the C, but this is some types of the rotation keys, and send it to the server, and the server can generate and uses the necessary rotation keys by itself. So the construction idea is the rotation operation. Actually, this rotation key is the bunch of the rotation key itself. So this is the bunch of the ciphertext encrypted rotated secret keys. So this X byte to R is the rotated secret key. So if we apply the rotation operation to the rotation keys, then this rotation operation is actually the homomorphic automorphism, like this. So if we apply R prime shift rotation to the R shift key, then we can generate R plus R prime rotation keys with this rotation operation. So this is the main idea of our work. Rotation operation to rotation keys. So, how can you generate this rotation key with all the rotation key? So can any rotation keys be used as the rotation keys for the rotation keys? The answer is no. So because the rotation keys have to be in the larger modulus than the side, which is the which have to be just rotated. It means that if the ciphertext in the RQ, in the modulus Q, then the rotation key have to be in the modulus PQ with the special modulus P. So this is the key modulus is larger than the ciphertext. So the rotation keys for the rotation keys have to be in the larger modulus than the conventional rotation keys. So this is the reason why we can give a hierarchy in the rotation keys. So this hierarchy, the hierarchy means that if there is a rotation keys in the higher level, then these rotation keys can be used to rotation operations and rotation keys in the lower level. So this is some formulation of the field that the hierarchy rotation keys system. So in the conventional homomorphic encryption scheme, such as the BFE or CTT scheme, then there is one special modulus originally. But if we have the K level hierarchy rotation key system, then there is the K special modulus. L is the 0 to the K maximum. So there is the hierarchy is in the modulus size. So if the modulus size is larger than some rotation key, then this is in the larger key level. And the form is the same with the rotation key. So this is the definition of the rotation key. And if you want to understand this, then please refer to my paper. And we have to generate rotation keys. So there is two algorithms. First is root-to-root operation. The root-to-root operation is the generation of R plus R prime L rotation key from the RL shift rotation key using R prime L prime rotation key. And you note that this rotation key for this root-to-root operation have to be in the larger key level, in modulus. So this is simple operation. This is the applying rotation operation to each element in the rotation key, as in the previous slide. Well, this is the abstract algorithm for this root-to-root operation, and this is the simple shortcut for this sentence. And there is a second algorithm, the pop-to-roll operation. The pop-to-roll operation is like this. Let's assume that only the highest key level rotation keys are transmitted to the client. And what is the basic source of the lower level rotation keys? Because the client does not transmit any lower key rotation keys. So this is the source of the rotation keys are the public key. So the main idea is the converting public key into the formal 0L rotation key. So the 0L rotation key is needless in the homomorphic computation. But if we have the 0L rotation key, then formally this is the form of the 0L rotation key. So this is very similar to the public key. Let's compare these to public key and 0L rotation key. The public key is the simple IFWD sample. But let's modify this formula. So this first line formula can be modified with this. the PL, QL, this is a budget. So A plus budget and this budget. Because there is a same S. So if we set this A plus the L IT budget to this element in the 0L former rotation key, then this is the 0L rotation key. Then if we perform the rotation operation to this former 0L rotation key, then we can generate this. We can generate the rotation key from this former 0 rotation key. So the public road operation is the generation of the RL rotation key from the public key using the RL prime rotation key. In the same way, the L prime is larger than L. So there is a former 0L public 0L rotation keys and prime rotation operation. So this is the diagram. So let's assume that there is a level 1 rotation key set, the 1, 2, 4, A, and the required level 0 rotation shift set is like this. But we have in that time we only have the public key. And with this public and multiple operation, then all required rotation key set can be generated with the server side. So the server can generate all required rotation keys from the public key. If you understand this concept, then the main idea in the paper is conveyed. So. And there is a 3-level rotation key generation scheme, then this can be generated with the next rotation keys. So in the offline, we can generate the level rotation key generation, and we can use this rotation key generation in the low level too. Okay, let's deal with this very fast. So efficient rotation key generation is the settings of generating order of this key generation. So note that this is the tree structure. So this main idea is the minimum string tree for the minimum operations for the operations. So the generating order is very important in this key generation. So there is the graph. The key we set some graph with the key shift require the shift, and then come to H, then compute to like this the number of the such as the power of 2 sum to the difference in the H. Then let's apply the Thames algorithm for the minimum string tree problem. Then efficient generating order can be generated. And the second is the hoisted rotation key generation. This is the very conventional idea in the homomorphic encryption society. So combining the decompression operation in the key switching operation. So this the whole runtime is reduced by the So I will show the simulation results. So let's go to the simulation results. So if there is no increase in the key switching operation to the cycle text, then if we perform the cycle text, perform the resonant tuning for the cycle text, then the communication amount is increased by decreased by the 4.7, and this is for the image head, the resonant 18, and the decreasing is more significant than this cycle. And if we allow some slight increase in the key switching operation, then this reduction is more significant. So it can significantly reduce the burden in the client. So thank you for this.
So let's fix it. Same improvement is going to talk about limit evolution. The worst the application is working. This is what is
Hello, everybody. Thank you for the introduction. And indeed, I'll be talking about polynomial evaluation today in a very interesting setting that appears during bootstrapping for the BFV crypto scheme. This is joint work with my supervisor, Rachel Player, and Joe. Yeah, so we're in the homomorphic encryption track, and I guess everyone has already seen like a slide like this that explains the idea of homomorphic encryption. Basically, it means that the server can perform computations on encrypted data without decrypting the data. And so the way we build homomorphic encryption, we usually include noise during encryption, and this noise is symbolized here by this temperature indicator, and it will increase during homomorphic operations. And if it becomes too large, decryption will fail or produce incorrect results. So to achieve fully homomorphic encryption, i.e. arbitrary long computations on the server side, we need a way to reduce the noise. And this is done using bootstrapping, that was already mentioned today as well, as introduced by Gen3. And the naive idea is, if the server could somehow get access to the secret key, he could decrypt the ciphertext and re-encrypt it, and this would like reset this to 0 or to very low. Clearly, the server can't get the secret key, but what we can give the server, or what we hope that we can give the server, what we believe, is an encryption of the secret key, which then looks like this. So the client has a secret key and encrypts the secret key using the secret key. And this gives a low noise encryption of the secret key, which can be passed to the server, or at least we believe so. And the server then homomorphically performs the decryption on some high noise ciphertext. And the output will be an encryption of the decryption. Noise will increase, but only compared to the noise of the encryption of the cipher secret key, which is very low. So if we choose parameters correctly, we can at least reduce the noise, by repeating this, perform arbitrary computations. We are interested in our work in bootstrapping for the BFV crypto scheme. It was also mentioned before, and it's one of the few commonly used FHE schemes. BFV and BGV are very similar, and I'm basically like unifying them here. Both are based on ring and WE. Work over a cyclotonic ring like this. So ZX modulo cyclotonic polynomial. Both BGV and BFV include messages and encrypt messages in R modulo T, where T is the plaintext modulus. And here you can note that for many parameters, the plaintext space RT, R modulo T, decomposes into a product of rings S1 to Sn. And we will have a look at these rings a little bit later, but I'm already mentioning it here. The main use of this is to allow for single instruction multiple data parameters. Ciphertext in the scheme, in both schemes, consist of two elements of R modulo Q, where Q is the ciphertext modulus and much larger than Q. And the secret key is a single element in our key. Both schemes allow the computation of addition, multiplication, and the action of Galois automorphisms on encrypted data, so it's homomorphic operations. Usually, I guess Galois automorphisms refer to the automorphisms of the number field, but since the string here, R, is the ring of integers in the number field and is fixed by all the Galois automorphisms, we can also write the Galois R over sets to the Galois R over the corresponding number field. BFV and BGP differ slightly in the decryption, which is of course relevant for bootstrapping, in the sense that BFV stores the plaintext in the highest significant bits of the value C0 plus C1s. So for decryption, you need to perform a rounded division. BGP stores it in the lower significant bits, and for decryption, we need to perform modular reduction. Yeah. So since we can perform homomorphically addition and multiplication, it is very simple to compute homomorphically the value C0 plus C1s. But both modular reduction and rounded division are not so easy to compute homomorphically, since we cannot they're not directly supported by homomorphic operations. And homomorphically computing this is thus sometimes called as digit extraction. Digit extraction refers to this function here, which we now say goes from set modulo p to the e to set modulo p to the e. Here we assume that the plaintext modulus is p, and e is an exponent, usually like a small integer, say 2, 3, maybe 10. And every value in set modulo p to the e can be written in a unique way as a p-adic sum, so the sum over ai times p to the I, where the ai's are either from 0 to p minus 1, or alternatively balanced from minus p half to p. And we now consider the function that maps such an element with set modulo p to the e to its lowest significant p-adic digit, so a0. Yeah, this function, it is not trivial, but also not too hard to see that this function can be used for modular reduction. Also, we use versus the BFV crypto system, it can be used to compute rounded division. So in fact, as it turns out, computing this function is really the crux to performing bootstrap. And hence there has been some research in how to best compute this function. And since we only can do addition, multiplication, and Galois automorphisms, natural way is to somehow write this function using polynomial interpolation. This has first been done by Halevi and Schub for HELIP, who invented the lifting polynomials that in some sense can compute this function. Later, by Chen proposed digit retaining polynomials that can also do this. Both ways interpolated in a slightly different way, and digit retained polynomials are better for certain parameter sets. However, we mostly work on lifting polynomials since they're simpler. The general setting is, however, the same. We have a polynomial in set x, and we want to evaluate it on a value, say x in set modulo PE. And it is also worth noting that since the polynomial is in some sense the result of interpolation, there's no special structure that we can exploit to efficiently compute. So we should focus on methods that efficiently compute arbitrary polynomials. Okay, just to finish the motivating section here, an overview of bootstrapping. Total for BFV, say, we start with a ciphertext, which has high noise and encrypts a message. And we first perform a modulo switch to get into this setting where we are in R modulo P to the E. And then we can easily compute an encryption of C0 plus C1s using an encryption of the secret PS, because our scheme supports homomorphic operations. However, as you can see, the digit extraction here, it can only work on scalars, as written here. So we're working in set modulo P to the E, but the C0 plus C1s is in R modulo P to the E. Hence, to perform digit extraction or
equivalently done rounded division or modular reduction, we first perform a linear transform and extract in some sense each coefficient of this noisy decryption. The linear transform itself is also a non-trivial topic. It takes a lot of time as well to compute it, but we won't go to that in this work because we just use exactly the same linear transforms. The step that we focus on improving is the digit extraction. Yeah, and after you perform the digit extraction, so in some sense remove noise from each tilde I, you can just plug the values together again and get the result, which is an encryption of the same value with low noise. This leads us now to our general setting of polynomial evaluation. And the two important things here are that both the polynomial and the value x that we want to evaluate it at homomorphically are scalars. So they are not in R, but general elements are of their values instead set p to the e. And the other important thing is that we are in that the ambient space that we are computing in is R mod over p to the e, or if we want to make use of the single instruction multiple data parallelism, it will be one slot, so one of these SIs. The SIs are Galois rings in general, but since I guess maybe not all are very familiar with Galois rings, we can assume for now that E equals 1, in which case they will be infinite fields. In general, E is not 1, but since Galois rings behave very similar to finite fields in many ways, it's easier to consider that situation for now, and I promise you that all the results generalize to Galois rings. Polynomial evaluation as such, and especially efficient polynomial evaluation, is an already very well studied topic with lots of work on it. But this setting has never before been considered. And that's, I think, quite natural because it's somehow a real setting. Usually, arithmetic in extension fields, say finite fields of higher algebraic rank, is quite expensive to compute, while arithmetic in set modulo n, set modulo p to the e is very cheap to compute. So you would never, like if you have the setting that f and x are already scalars or overscalars, then you would never think of going into a ring with high algebraic rank. However, in our case, this high algebraic rank we get for free because it's provided by the homomorphic encryption scheme. And so it makes sense to think about the situation that this is the case and ask the question if we can use it to do better than previous techniques. And at the core of our main idea is the norm in the field extension, fp to the d over fp. The norm is generally defined as the product of all automorphisms of the field extension applied to alpha. And since the Galois group of finite fields is generated by the Frobenius automorphism, we can regulate this product here. And I made two important observations about the norm. The first is a standard result from Galois theory, and it goes as follows: if we have a scalar value, so x is a scalar here in fp or in zp, and a non-scalar value alpha in fp to the d, and in fact I didn't mention here, we need alpha generates the whole finite field, but that's the case for most alphas in fp to the d. But in particular, alpha can't be a scalar. In this case, we have that the norm of alpha minus x is equal to the minimal polynomial of alpha evaluated at x. This is a standard result from the corollary from the fact that the norm of alpha is equal to the constant coefficient of the and as you can already see that this relates in some sense to our setting because we evaluate the polynomial, particularly the minimal polynomial of alpha at the scalar value x. And the second observation is that we can compute the norm, and in fact we can compute it much more efficiently than just naively performing this product. Naively performing this product will take p-1 multiplications, but in fact we can do in log multiplications. And the reason for this is that the norm has, in some sense, functional factorization. I think it's easiest to see this in form of this kind of recursive algorithm that I hinted at here. So if we start with alpha and compute alpha times pi of alpha, alpha 1 times pi square of alpha, alpha 2 times pi to the 4 of alpha, and so on, and use the fact that pi is a ring automorphism. In particular, it commutes multiplication. We can like pull out the products outside of pi and get then the product from alpha, pi to the pi of alpha, pi square of alpha, and so on, till pi to the 2 to the k minus 1 of alpha. And from this follows that alpha d log d, alpha log d will be the norm. And we only use like log d multiplications correctly. This observation is on its own quite well known in FHE literature, although it is usually used for the trace. The trace is like the sibling of the norm, they will replace the product with a sum, and it has already like lots of applications. The norm has been more seldomly considered, but yeah, you can use this technique to evaluate both norm and trace very efficiently. Yeah. So using these two observations, we are already closing in to our end result. And in fact, it follows quite naturally from these two observations. So if we find some alpha such that the minimal polynomial of alpha is the polynomial we want to evaluate, say the lifting polynomial, then we can easily use observation 2 and observation 1 to evaluate the lifting polynomial in only logarithmically many steps. As a comparison, previous work used the Patterson-Stockmeyer method, which takes 2 times square root of the degree many multiplications. So in this case, we improve from square root d to log d. If we find such an alpha, this is like the condition. It has some implications. For example, if the minimal polynomial has degree at most the degree of the field extension, so the degree of the polynomials we can evaluate as something bounded by the degree of the slots. But then we argue that if this bound is indeed fulfilled, if the degree of the polynomial is not too large, it's quite likely that we can find such an alpha. And in fact, we show that we can indeed find such an alpha in many parameter settings that we're interested in practice. Also, this technique might be usable in many other settings, not just in scrapping, but yeah, whenever we want to evaluate a polynomial on scalars, a scalar polynomial on scalars, you might think about, might be possible to use this technique. So it's of interest, might be of interest in scrapping. However, bootstrapping is like very important functionality, so it seems to be a natural way to test it. And in fact, we implemented the whole thing in a certain setting and beat the times of previous work. So our setting uses power of 2 cyclotomic polynomials, where pi of n is x to the capital N plus 1, where capital N is power of 2. These rings that result from this are common in the literature. They are not the only considered cases, since they have some disadvantage compared to other cases, but also some advantages. So it's quite an unclear question which rings are the best. These here are certainly important. They have been previously considered by Chen Han, and they are also contained in the FHE standard. So they are not an example, not an exotic situation. And then here, the other parameters we choose as p plain text prime 257 and as exponent 2. And this gives us 128 slots, and each slot has algebraic rank 256. And implementing this in the Microsoft Seal library gives us these timings here. So I also included the timings for the linear transforms, which, as you can see, are also quite high. But in fact, these should be approximately the same as for previous work, since we didn't change the algorithm for linear transform at all. But we improved the digit extraction step here and improved compared to have an improvement of more than 50% compared to the implementation of Chen Han, which I think is quite impressive if you consider that we expect the time for linear transforms to be about the same. We can't test that since they didn't publish the source code, but yeah, that's what we would expect. And I think this is quite nice numbers. Finally, I want to talk a little bit about future directions. So there are some other parameters, I think, that we haven't yet considered. In particular, where E, where if the plaintext is not a prime, but a prime power, you should usually use these digital tanh polynomials, as they have certain advantages in this setting, and they have been proposed by Chen Han and further optimized by various authors. And it would be an interesting work to try to combine this with our techniques of Galois evaluation. And other applications will also be interesting. As I said, we might use our techniques to implement to evaluate other kind of polynomials in other situations fast. We also have some ideas on how you could evaluate multiple polynomials at the same point, but we didn't yet explore any possible scenarios where this would be important. But searching for this kind of applications will also be an interesting direction. That's it. These are my references, and I thank you all for your attention.
Yeah, I was wondering whether the recursive algorithm, it seemed to be inherently sequential, log depth. Is that an issue at all, or is there a way to maybe have it not be higher depth?
It's inherently sequential, yes. And I think in some sense, yeah, so are you worried about parallelism and performance or about multiplicative depth?
And multiplicative depth.
Okay, yeah. So in fact, this is, I think, a very insightful question. It is inherently sequential, but I think this is absolutely necessary. So our polynomial has degree D, and it seems impossible. I think it can be proven to be impossible to evaluate a polynomial of degree D using less than multiplicative depth. So I think it's
T is equal to
one.
So I believe that. Is there any chance that, I don't know enough about this area, but that you could supply the alpha i's as sort of an advice and reduce the depth through that?
I haven't thought about it too much. I still think that it will be impossible, because it's slightly complicated in the finite field case. At least over an algebraically closed field, it's very obvious that there is absolutely no way to compute a polynomial unless log D multiplicative depth. In this case, there might be some options. I'm not sure. My intuition tells me that it's unlikely.
So I have a question about polynomial evaluation. It seems for rank as high as 256, then your method using automorphism brings some benefits, and for low rank, that's not the case. Do you have some idea what the intersection would be, like which order?
Yeah, I have a few ideas, but they're not very. I haven't taken much shape yet. I think that is an interesting open question. I can't say anything more about this.
Thank you.
ce type de workbench.
Hey, hello everyone, glad to be here. My name is Alain Passelègue, and today I'm going to talk about M1 hash function bootstrapping in less than 7 milliseconds with quasi-constant algorithm multiplications. It's a joint work with Homomorphic. So let's start. So first, thanks to the prior 3 talks, I think you are quite familiar with APG already. So what is APG? Essentially just allows basically outsourcing computation, like we can build very quickly. Actually, let me just time. So I want to briefly highlight the applications of APG just to show how powerful APG is. And the most popular, I guess, application is the private computing, and it's well exemplified by privacy-preserving machine learning. For example, as you just heard from during this talk, another popular line of work, another popular line of application is that it can be applied to realize other classic cryptographic primitives. For example, private information retrieval in this MW22 paper. This is just as an example, and or private set intersection in some law paper, 2021. And another line I want to mention is that recently there are some applications in private messaging and or blockchain systems. And for example, the ambiguous message retrieval by LT22, group of ambiguous message retrieval by LTW23. And there's another work, just an example, like APG-based smart contracts in SWA23. So there are so many interesting applications, and you can see that all these papers are very recent. So it really shows that APG is a very important and well-used, widely used primitive. Okay, with this motivation, let's dive into the work. So let's start by doing some history. So the concept of APG is first introduced by Rivas, Aldoman, and Tertorlos in 1978. And it was first realized by Gentry in 2009 in his groundbreaking work. Then the first real practical line of APG work is BGBBFE, as you have already seen in the prior talks. It mainly focuses on the finite field operations. And the second practical line of APG work starts from GSW, and we have Vue, APG, and so on. And they mainly focus on binary operations, and they also have an important feature called functional programmable bootstrapping, which I will explain in a bit more detail in the next slides. But this will be the main focus of our work. And the third line is just the third line is CPKS, which focuses on fixed point arithmetic, as you see from Jung's talk. And okay, so our work focuses on bootstrapping and what is bootstrapping and why is it important, as you already seen from Simon's talk. So basically each ciphertext has some initial noise, which is denoted using this semicolon N1 notation. I promise in the future I will use a temperature indicator, which is probably better, but please bear with me today that I'll use this notation. So if you evaluate some operation over the ciphertext, for example, if you evaluate function f over this ciphertext CT, you will get some CT prime. This CT prime basically gives you an encryption of f and m with some noise, say 10 numbers. It's much larger than the input noise. And after the input noise arrives some threshold, the bootstrapping is needed to bring down the noise. So we just use boot to denote this operation, and we get a CT star. CT star basically encrypts the same message as prime, and the noise level brings down to, say, roughly the same as the input ciphertext. Okay. This allows us to evaluate a function with arbitrary amount of operations. That's why we fully implement. Okay, so a bit more background on FUTVG. This line of work focuses on binary gate bootstrapping. And so given two ciphertexts, CP1, CP2, each of them encrypting a single bit, B1, B2, we want basically to compute a ciphertext CP NAND that encrypts the NAND of the input 2 bits. And we want that the output ciphertext to have roughly the same noise as the input noise. Okay. So why NAND? Because first NAND is a universal gate. So with NAND, we can compute some arbitrary circuit. And second, NAND is actually not a hard requirement. You can use it for other gates. Used like for all the existing works that I know of, can be applied to other gates, except for XOR, which has some caveats, but it's not the focus of the talk today, so I will skip that. The second important feature of the TFG line of work is that it supports functional programmable bootstrapping. So for simplicity, I'll just call it functional bootstrapping. You can know that it's just equivalent. So what it means by functional bootstrapping basically means that given a ciphertext encrypted, now the message encrypted is in ZP instead of single bits, and we want to compute the bootstrapping operation boot with a function f, and output some ciphertext denoted as CTF, and this CTF encrypts the message f of m, and with the same level of noise. This means that we can evaluate a univariate function over the message m without increasing noise. So it's important that this is a univariate function because it doesn't support multivariate function arbitrarily as like most FHE operations. So the focus of this work will be batch bootstrapping. Batch bootstrapping simply means that we work over n NAND operations or evaluate f over n different ciphertexts instead of just one. So, okay, and it achieves better MLX efficiency. Okay, so a bit more of history. So this binary gate bootstrapping it first starts from the few work, and then it's improved by the TAPG work, and recently there's another work by Paul. So these three works focus on a single gate binary bootstrapping. The cost is roughly quasi-linear in the security parameter, and so for each ciphertext, it's counting the number of polynomial notations, and practically it takes more than 10 milliseconds. So although it seems to be quite fast, but it's only a gate operation, so it's pretty much almost magnitude slower than that. So to achieve a better efficiency, Chantal and Sorrell in 2018 suggested to use a batch. They proposed a scheme that for these semi virus talk that they have some huge constants 3 to the epsilon hidden, right? So although it's theoretically asymptotically faster than single gate bootstrapping, it's concretely not very helpful. And then in 2023, this work of GPL and the MKMS, they have removed this 3 to the epsilon to just epsilon. And another work that's mentioned out this year have further reduced it to asymptotically quasi-constant number of polynomial multiplications for each ciphertext. But okay, but as mentioned by Barry, like whether it's really practical, it's actually open problem, so we don't really know that. And then it's our work. So our work achieves basically the same asymptotics, and practically it's like one order, at least one order of magnitude faster than the single gate bootstrap. And but I have to mention that there is one limitation of our work, which I will mention in the next slide. So next slide we will talk a bit about history for functional bootstrapping. It's also first proposed in the field and then improved by TPG. For each functional bootstrapping, it takes a couple of seconds to evaluate over 7 bits of message. One major limitation of this work is that it assumes that the most significant bit is the input message to be 0. This is a huge limitation in practical applications because you don't really know what the message is. So in 2021, there were like 4 works, CLOT, FDMP, MP, and FODEP. All of them focuses on this function bootstrapping, and their runtime is roughly the same as prior works, actually a bit slower. But their like contributions that they remove this limitation. Again, we're now in the batch world. So we have this GPL and MKS MS work again, and they are practically much faster. And as mentioned by Barry, it takes like so it takes seconds to for like 7 bits, but it's already practically much faster than a single function bootstrapping. And lastly, our work. Still, our work is well, it's kind of spoiled already in the title. It takes 12 to 7 milliseconds to do a function bootstrapping for a single ciphertext with something like 9-bit precision. So you can see it's like 2 to 3 orders of magnitude than compared to prior works. As promised, the limitation, our security assumption is indeed strong. We require that the modulus noise ratio to be super-polar, which means that our parameter is more wild than all prior works, which don't have this problem. I guess in practice, that's a potential. Okay, so, oh, sorry. There's one common limitation of all these works I mentioned on this slide that I want to comment, is that all these works have a runtime that's basically linear in the plaintext space. So if you want to do a function bootstrapping, the runtime is basically in P if you have only log P bits for the plaintext space. To my knowledge, there's no universal solution, and it seems to be inherent in the sense that if you want to evaluate an arbitrary function, like mapping 2 P points to P points, you need P operations, right? So it seems inherent, but there are solutions for some types of functions. For example, in the MP work, they achieve like only almost linear runtime in terms of number of bits of the plaintext space for sign functions. With this history, let's go to a bit of a background. So LWE encryption, I believe with all these talks, you're probably already quite familiar with LWE encryption. So let's very quickly go through this. So we have LWE encryption has an A-B part. So A is a vector, B is a Q element. And we have a secret PS. So the encryption is essentially you compute the A part in the product with B with S, and then we want to encrypt, let's say we want to encrypt 0, 1, or 2. We just encode 0, 1, or 2 in Q or 3, Q or 3, and 0. And then we add some small noise E, and this is the B part that we're computing. The ciphertext is A part plus the B part. And the decryption is also very simple. We take this B part, B minus the inner product between A and S, and we do what we call a range check. So range check basically means that we want to map something back to 0, 1, 2. How do we map it back? We just check if it's in this range. We will use we will return 0. If it's in this range, we will return 1, and otherwise we will return 2. This is, if you have time, you can check that this corresponds to the way we encrypt, but let's keep the details. So yeah, one more thing about LWE encryption is that it is weakly linearly homomorphic. It means that if you add 2 LWE ciphertext encrypting message M1, M2, you will obtain another LWE ciphertext encrypting M1 plus M2. Why is it weakly? Because basically we only the addition adds up the noise. We can only perform a limited number of additions for LWE ciphertext. And some background on BFE. As you probably recall from Simon's talk, so it basically allows homomorphic evaluation of the ZT, where we use T as some prime. So T is some prime part, and we don't have an excellent case. And T we call it plaintext modulus. And it can evaluate n ZT elements at the same time. This is the CD feature that's mentioned by Lulu. So if we, so the BF2 ciphertext just encrypts M1 through Mn, so n messages in ZT, and then we evaluate a function f over the ciphertext, we get CT prime again, and then the CT prime is encrypting f of Mi, where Mi is the messages encrypted, and it has some non-standard standards. Okay, so the ciphertext is a ring element ciphertext. It basically is just, it has two ring elements. I guess I'll skip the details as it's already been introduced, and but it's actually not super important. I will say what's the takeaway. So encryption of the ciphertext of BFE scheme works as follows. So you sample some ring Q elements, encode some message you want to encrypt into a polynomial in ring T, and then you compute this this B part. The main takeaway of this is that BFE essentially has almost the same format as LWE ciphertext. Except you just replace the underlying ZT or ZQ with this ring T. With this ring BQ. So this will be used in our work to achieve batch. Okay, so with all this in mind, so we can start to talk about our work. So the setup, we start with 2n LWE ciphertexts. The secret key length is small n. So this small n is smaller than big N. And the ciphertext modulus, the Q, we have to set it to equal to T, where T is the plaintext modulus of the underlying BFE scheme. This is important because we need to operate over ZT, the ZT final field, so that we can get 3 modular. So then we set plaintext space P equal to 3, what it means that basically we mean that the LWE ciphertext either equals 0, 1, 2. Okay, so we have basically this 2n LWE ciphertext, and our goal is to output n LWE ciphertext such that each ciphertext is encrypting the NAND of the input to ciphertext, the messages encrypted by the input to ciphertext, without encrypting the noise. So step 1, what we do is first we add this ciphertext pairwisely. So if we add them pairwisely, what do we get? We basically get a ciphertext that's called CTI. That's encrypted message MI. That MI is basically the summation of MI1 plus MI2 and mod 3. So we do mod 3, and it has a slightly more noise. There's 2 level, for example. And this means that message I is equal to 2 if and only if the input pair of messages are both 1. This is a very trivial example. Now, step 2, we basically use BFE to homomorphically decrypt this ciphertext. So again, this is the decryption circuit. We first compute a linear transformation. We do B minus AS. And this, we can see, it's just a linear transformation, so it can be easily done by using BFE. The hard part, I would say, is the range check. Range check requires some technical comparisons, which are not inherently supported by BFE schemes. But it is also easy because the key observation is that any function over ZT can be represented as a degree T minus 1 function. So basically, we want to interpolate a function, let's call it range check poly, RC poly, mapping from ZT to ZT, such that for all messages I in ZT, RC poly I is equal to S. So we interpolate this function of degree T minus 1, so it's basically equivalent to the range check function. Of course, this is not yet the end of the story because what we really need is the NAND gate, right? So we need to map basically 0 or 1 to 1 and 2 to 0. That's the definition. So we change this this range check function to a range check NAND function, and basically we map this 0, 1 to 1, otherwise to 0. But we don't directly map to 1. We map to T over 3. TO3 is like the encoding one, and the Z3 case. And again, then we interpolate the function we call RCN poly, and after evaluating this RCN poly, we basically get a ciphertext, a BFE ciphertext that includes a vector that has, say, 10 levels noise. Basically, it satisfies the following property: mi equals to 0 if both mi1 and mi2 are both 1. This is the requirement of the NAND gate. And then mi is equal to t/3 if either of them are 0. Now, the next question is that we have some BFE ciphertext. How can we transform a BFE ciphertext into n LB ciphertext? Yes, our goal is that to output the ciphertext that's basically the NAND of the input ciphertext. So we need all of them to be LB ciphertext. But luckily, this is very easy. There are standard ways to transfer ring LB ciphertext to LB ciphertext under the same key, which is widely used in our works, other works. So I will skip the details given the time constraints. So please just leave me for that. And so now we have basically n LB ciphertexts like of the following form. So they have the form of vector A plus scalar B that's in D bit Q and have length big N plus. So, and it's also encrypted under the BFE secret key. It's encrypting either 0 or TO3. Our final goal is to obtain LB ciphertext that's A prime B prime that's in DT, where T is much smaller than the big Q, and then it's under the LB secret key S instead of the BFE secret. And it should encrypt a bit 0, 1 in Z3 instead of 0, TO3 in DT. So this transformation can be done by using key switching and module switching. Key switching basically means that you can transfer a ciphertext with secret key for BFE secret key and transform it into a LB secret key. And module switching essentially means that you can transform a ciphertext from ZQ to ZBQ to VT. I will also skip the details, but these are also standard techniques. And after module switching, the message encrypting TO3 will be mapped to 1 and 0 will be mapped to 0. To summarize, we have 2n LB ciphertext as inputs. We add them pairwise, we homomorphically decrypt them using BFE, and extract n LB ciphertext from this resulting BFE ciphertext, perform a key switching and module switching, and then we're done. Like, we finished the NAND gate part. And note that this is also easily extendable to arbitrary binary gates if you just replace the underlying decryption circuit. So that adds a bit more flexibility. I also have some techniques are standard, some techniques are slightly tailored for our work, but these are optimizations, so I will skip this slide as well. Okay, I want to spend a bit of time on arbitrary function evaluation. As mentioned, this is where our basically really shines. So for functional bootstrapping function evaluation, it's an important feature of the HT line work. Now the input LB ciphertext are not bits, but messages encrypted in messages in ZP. So again, what we do is we first compute B minus AS, and then when we evaluate the function, our goal is to evaluate some function f mapping ZP to ZP, right? So we want to represent this function f using some function f prime. So what this f prime is, this f prime is basically that for all elements in ZP, we have a f of x, f prime of x equal to f of branch check. So we're basically replacing the branch check NAND function with this f prime. And then we homomorphically evaluate this f prime on this B minus AS. And this gives us the BFE ciphertext that's encrypting f prime of this encoding. And again, we use key switching and module switching, map them back to LB ciphertext. This ciphertext encrypts f of m as we need. Okay, lastly, let's quickly look at the benchmarks. So for our work, it's easy to see that it's much faster than the single binary gate bootstrapping in terms of throughput. The latency, of course, is much worse. So this 1.5 and 48 on the side is something not in our paper. It's it involves some techniques that are not mentioned in the paper, but indeed we can even further optimize our results into 1.5 milliseconds per binary gate, and we are aware that some team is doing some additional optimization that can easily bring this down to less than 1 millisecond. So you can see that it is much faster. And lastly, for the part where we really shine is the function bootstrapping. So as you can see, it takes 6.7 milliseconds for a 9-bit binary for a 9-bit lookup table for function bootstrapping. It's much faster than any of the priors. The only one that's slightly close is the 409 one, but that one has some weird input assumptions, so it actually has some even more real-world overhead if you want to apply applications. So you can see that our work, no matter for 12 bits or 9 bits, we are 2 to 3 orders of magnitude faster than any. I have some discussion that involves some, like say, future works. Since I'm basically out of time, I will just have those skipped. And that's all. Thank you all very much for listening. The paper's link is here. Happy to take questions. Thank you.
Hi, thank you very much for the talk. Are there concessions you can make in your scheme to get rid of the super polynomial modules?
Yes, we think about this. So if we I think inherently no. But we can make it smaller. So right now the ratio is basically n to log n. We can probably make it n to log n if we apply some techniques from Simon talk. I'm not exactly sure, but it might be.
Thanks for your presentation. I have a question. You want to connect with threading strategy. You know, example for bit strategy or functional strategy. We have circuit strategy that it can convert LW to RJW. Can you give a trick or on-type circuit structure because it is more complicated slower.
Yeah, I think it is possible to achieve that. It may be more techniques, but I haven't thought about that in detail.
Right. So let's fix the position again.
Actually,